Okay. So did somebody try to install the environment? If you try it on Mac, it's probably going to fail because this Mina out of Vina doesn't have compatibility from Conda to Mac. So sorry for that. You need to use the Colab. And otherwise, you need the Linux. I don't know Windows, but hopefully the environment is going to be fine with that. And it's going to take a while. Yeah, perfect. 2 minutes of awkward silence because we need to update the environment. So the point of this presentation is just showing you how to build a little Docker docking pipeline and actually training a Gaussian process on really simple fingerprints. We're going to use SFP from basically yesterday, and we're going to build an active learning loop to basically avoid doing a docking call. Most of the problem is that docking is not really that expensive. We are using the dataset from yesterday of 24,000 compounds, but Colab is really slow at this kind of call. So an active learning loop only for using Colab seems fine enough for a lab. This kind of loop in active learning is basically can be applied in lead optimization and all that kind of stuff. So I think probably it's fine enough. But yeah. Taking a bit. So yeah, while testing is actually installing, I'm just gonna cover a little bit of theory. So we're gonna use the same AGFR from yesterday. Is a 6V as a structure is a 6V chain. I linked the PDB-ID. And basically, we're just using that because we know all the compounds bind in the hinge section as an ATP binder. And you're going to see that a lot of calculator from a scoring function and also from the active learning loop is strangely low as really good affinity, mostly because the dataset that we have from yesterday are basically enamine compounds that are made for the kind of intersection in the binding site. So we don't expect any bad results from that. But goal of the lab is basically explaining a little bit of the workflow for preparing a docking and actually do the docking and show a little bit of the results on the docking and to build an active learning based on optimization loop to find the high binding affinity candidates from a supposed molecular screening that we are doing. Almost finished. Nice. So yeah. So for theory reason, I'm just gonna talk a little bit about the free energy and molecular docking. I kind of showed before docking as something that predicts some kind of affinity, but I'm talking about kind of affinity in a strange way. Usually what you have from docking is a docking score, and then from the interaction that the docking engine has inside, it's going to try to predict you the affinity. So basically, docking engines are grounded in the physics way of the composition chemistry, and Autodoc Vina pairwise function is going to just calculate some intermolecular interaction. It's going to just check what type of interaction do you have, if you have a H bond, some kind of stacking, and this kind of interaction that are more physically rooted, and from that it's going to try to basically predict a binding free energy from just some kind of weighting, and to actually dock the molecule inside this kind of engines use this kind of score as basically their main energy function, and they're basically going to try to optimize in different kind of ways to have a higher score or a lower binding free energy. Usually it can be from some Monte Carlo simulation. They can grow the ligands inside the pocket, but most likely, as we are doing with Smina or Autodoc Vina, it's going to be the docking engine is going to use just a genetic algorithm that is going to optimize. So yeah. Okay, everything is solved. Perfect. Okay. So yeah, just to give you a more theory approach on the binding free energy, all the drug discovery pipeline is basically to calculate these important properties of a molecule that interacts, of two bodies that interact basically, and it's just an equilibrium reaction between a protein and a ligand. So it's a dynamic trade-off between the dissociation and association that a ligand has with a binding pocket, and is basically proportional to a binding constant that you can calculate from it is K in, K off. But basically what we are calculating, what we are interested on, is basically a difference in binding in free energy between an unbound state, so a ligand that is really far away from the protein, that doesn't have any interaction with the protein, and the ligand that is inside the pocket, and that's what giving you the binding free energy that we are looking for. Okay, so as a workflow, it's a really simple workflow. We are doing rigid docking. Usually, right now, most of the docking engines has some degrees of flexibility also that you can enable. So both the ligand or some sidechain can be flexible. In this kind of case, we are just going to do normal rigid docking, and we're going to just check a little bit on the workflow and what you need to do to actually prepare your a little bit at least your ligand or PDB to actually be usable on Smina. But most likely you're gonna check your PDB file, you're gonna check that everything is correct, you're gonna remove your ligand, water molecule that you have inside and everything, and something like that. You're gonna protonate, you're gonna add your hydrogen at the correct protonation and pH. You're gonna convert in the your specific file format. Mostly, if you use Mina, is PBDQT. And then you're basically going to run the docking engine, and it's going to just do a conformational sampling of the molecule inside the protein pocket that you most likely have told him to do what protein pocket you have. And it's going to just score the generated docking poses, and then you're going to do some post-processing. And as my PI actually used to say on everything that it's molecular dynamics related, visualize the result, because it's really easy to actually get the better result with statistical analysis, but the most common results that are not really easy to see, they're too easy to understand from mathematical standpoint. You can just basically get a quick look at the molecular dynamics or the result of PDB, and you can probably get it away. Okay. So basically, the workshop structure is basically the data where we have the PDB that you can download from the website. I already prepared the PDB that we're gonna use, and gonna show. I'm gonna at least tell you a little bit what I did to actually prepare, and you're gonna have the library from tomorrow in the data folder for yesterday from the data folder. You also have a Python file with some coding inside. It's mostly for parsing molecules in different kind of formats, mostly boring stuff, and how to actually call the docking engine, but it's basically just a sub-process call with the correct flag, and everything is mostly parsing files around. Okay. So first thing first is that you most likely have your PDB structure from your chemist, your crystallographer, and you're gonna have to check inside what do you have. Most likely you have a ligand binded to your region of interest. So first thing is basically preparing the PDB. Normal preparation is basically at least remove the ligand, and from that ligand binding, you probably have your binding region of interest. So in this kind of case, it's just MD3J and just telling it to remove everything that is not protein and not water. So and save it as a ligand PDB. But preparing a PDB for docking purposes is multiple step. It is a multiple step things. It depends on the phase that you are. Almost every time removing the ligand from the PDB file, you want to delete most likely the water molecule that's around. You want to convert the residue to standard residues because these kind of programs are really, really finicky sometimes, and they don't like having some kind of atom types or atom name or residue names in another kind of format. And you want to basically standardize the kind of residue, complete the side chain, do a capping on the terminus, and all this kind of stuff. Important is also that you are adding the hydrogen with the correct protonation state, usually pH 7.4, but there are some residue that are more tricky, so a more expert chemist can always help on choosing the right protonation state for some of the residues and adding charges to the protein. In this kind of case, I use the Gas-Tiger model to actually add the partial charges. It's something that you can do relatively quick and relatively easy, even on Python, just by RDKit or OpenBubble. And I also changed the residue to basically amber FF14 SB names. This can be done with basically everything. I use a lot Chimera to prepare this kind of stuff, and it's a nice program, I guess. But you can build an automated library just by using OpenMM and PDB Fixer for this kind of stuff. So just to show a little bit of our stuff, probably obviously gonna fail now, or maybe the Wi-Fi is just bad. Okay. So this is the protein of interest. It's in new cartoon settings, so you can see basically the alpha chain and everything from the protein. And in wireframe is basically the added hydrogen and residue. And we're gonna try to basically create the ligand that we extracted from PDB and rebind it inside the PDB. The binding site that we found in the PDB. So to do that with SMINA require PDBQT. Translating PDBQT molecule from RDKit to PDBQT can be a little bit of a pain sometimes. So what I recommend is basically reading you can do it OpenBubble or reading PDB format, or if you have a molecule, you can basically just try to translate with a mol2block function that RDKit has. And you're going to prepare basically the ligand by loading, adding the hydrogen, making 3D, creating a conformation, and basically calculating partial charges and saving it. So yeah, really small, really small. This is a little bit more. It is written better in the preprocessor class that you can find in workshop utils. But here it's basically just doing the same things for the PDB that prepared. If you try to run exactly this function for the normal PDB, you're probably going to get an error due to some strange residues that is inside, and also for the ligand that we didn't remove in this kind of case. Why it is important to have the ligand in this kind of cases that it is because we're not doing blind docking, so we know where our binding site is, and we're going to create a binding box. The binding box is just a cube or a rectangle. It's literally a three-dimensional area where we're telling the docking engine to try to dock the molecule. So if you don't know the binding box from the crystal structure, you're a little bit in a bad position, because blind docking is a complex thing to do. And you can try to check your binding site in multiple ways. You can use other kind of software like Fpocket. You can do some solvent accessible analysis. You can do some molecular dynamics with the fragments to actually understand where some type of pharmacore can bind in your pocket. But it's the binding site research is tricky, and you can also try to use some other approach like machine learning, like Equibind. But if you are in a certain-based drug discovery pipeline, you probably have at this point a crystal structure, so could be okay. If you're more into the discovery side, it's going to be another type of problem. But in this kind of case, it's just a matter of loading your PDB that was binded inside your pocket. In this kind of case, if you use MD2J, just remember that it is in nanometers when you load. So usually PDB are always in angstrom. So quick check that you are doing everything correctly. Otherwise, you're gonna find that everything after the docking is gonna be outside the protein because it's a different kind of system. But it's basically just keeping the center of geometry and just building a random docking box with a maximum size. So in the docking, there is some other parsing. It's just an utilities structure to basically call a subprocessor that is going to call SMINA. You can check around if you want to implement other flag. You can just try to call SMINA help, and you're going to see that has a huge number of flags that you can set it up. In this kind of case, it's really simple. We're just going to dock, I think, five poses in a rigid docking way at this kind of receptor. We're going to use this kind of receptor to basically build that activation loop. It's going to take a while. So also inside you can find how to parse the output. It's usually this kind of software they give you a score for all the poses, and they're going to write in a single file, usually SDF or PDB, all the poses with the correct information. So you are going to have two PDB files or one PDB files and one SDF files that are basically your structure and the comps that you just poses in various conformation. Yesterday it seems to more fast than now. Okay. Well, if somebody is using Linux and is following along, probably already ended this cell, and they can just visualize the docking structure on the next cell. But I'm stuck here. Otherwise, I can proceed. So sorry for making you wait, guys. I can totally feel the silence, but that's why I'm using an active learning loop, even if you're using docking, because collab is not collaborating. Thank you for the sweet music, Johnny. So guys, are you enjoying Montreal? Yeah, this is big computational chemistry, guys. Telling you. Oh yeah, go for it. Oh no, too late. You made the docking move. It's literally Schrodinger. As soon as you want to do something, it's gonna do something. Like, I'm sorry. that's the beauty of computational chemistry, quantum level. But yeah, as you can see, the affinity are really, really high or low. It depends on how you actually consider this kind of values. But that's mostly because the screening library that we are using is literally optimized for this hinge region as a binder. So we don't expect any really, really bad docking score. Just as an information, the big molecules that I showed before, the really big one that I basically forced as a nail inside the pocket, as a binding affinity predicted of 77 kilocalmol, so quite bad, obviously. But yeah, just to show, it's basically we docked right into the position that we wanted. And so just to load a little bit more of the position, you can, as molecules, and I'm just plotting as a 3D confirmation from RDKit, and they're just there. So I'm now scared to run another docking case, but it's mostly for try with some real molecules. Let's try, and we're gonna try to ask to answer some question in case while we wait. We have time.
So while it's waiting, maybe we can take a few questions if there are any. Yes.
So I was just wondering how to define. Dang.
Yeah. No. Don't worry. Ask it because.
Yeah. So I was just wondering how to define like the binding box. Do you just like go into like a PDB viewer and like visualize?
So for the binding box or bind.
Yeah, like
So,
how to actually find the coordinates of the box.
So the binding, if you have a PDB with a complex structure, so you have the binding side, you can basically just grab the coordinates of the complex that is binding, and that's basically where you can build your binding box. There are different ways to actually build this kind of binding box. I did just the basic stuff that is basically grabbing the center of the ligands and just doing a random box. But most likely you want to do a little bit more tricky stuff like see how much volume it is in the little pocket, but shouldn't be an issue. If you don't have that, so you're basically doing some research, some exploratory analysis, and you need to find a binding set, we are another in a different issue. That's more tricky, and docking is not going to help you on that. You can run docking randomly, you can, but you need to always check. I will say that in this kind of case, use a different, before going to docking, you can use something different like fpocket that's basically trying to tell you where are the binding site. In this kind of case, you basically have the coordinate of a three-dimensional mesh, and you can just basically grab that, and you can try to bind on different binding boxes at the same time. And so you're going to have more poses, and then you go your output analysis as a post process.
Gotcha. Awesome. Thank you.
Okay. But yeah, what I'm doing is basically loading the data set of yesterday. Johnny, be wary because I'm going to dock 5 molecules. Until now, it was 1 molecule, and we waited a lot. But just calculating some fingerprints and docking multiple molecules. So, okay, question, because we're going to be here for a bit. Or music. Perfect.
Any questions?
I have one. Do you guys see it put in that yesterday? No? Okay. Yes, where? I will say Mapouly-Molière, near Le Banquise. Mapouly-Molière. My wet chicken. It's really good. Mapouly-Molière. If you search for La Banquise, is the famous place. Literally in front of that, there is Mapouly-Molière. Go there, guys. Okay, we docked everything. So just to check, we have other affinity stuff. Oh, the Putin actually made people talk. Nice. And just to visualize the ensemble of first the 3D molecules that we docked, you can find a little bit of information. They're really small. They are from the data set. They're quite easy to fit into this kind of pocket. But more interesting is that every molecule should be actually docked. So yeah, we have a nice ensemble of molecules in the pocket. And that's, I guess, it's mostly all for docking. And now we're gonna get in the most interesting part of the talk, that is the active learning loop that you can build. And I'm gonna let Johnny do the presentation. Thank you, guys.
Awesome. Thank you, Cristian. So for the next part of the lab, I know it's 4 p.m., but this is the last part of the summer school. So I'd ask everyone to try to pay attention for the last little bit. But I'm excited to welcome up Stephan Thaler, who's a research engineer at Valence Labs, also working with Prudencio, but more focused on machine learning for atomistic simulations for drug discovery. Before joining Valence Labs, he completed his PhD at the Technical University of Munich and Harvard University under the supervision of Yulia Zavadlav, where his research focused on training neural network potentials for molecular dynamics simulations. So let's welcome him up onto the stage, and he'll take over the last half of the lab.
Yeah, thank you very much for the introduction, Johnny. I'm pretty much gonna go and continue the presentation. I've got the pleasure of showing you or walking you through the very simple active learning cycle that we implemented here in this lab. So in the last lab yesterday, you've already seen how you train a neural network model or machine learning model in general in a supervised learning manner. And for that, you've already seen like two main components, which is your labeled data and then your machine learning model. Now, the problem with drug discovery is that we are usually in a data scarcity setting. So we don't really have as much labeled data as we have like in the image domain, for example, with ImageNet with millions of pictures of bananas. So we really need to make the most of the data that we have. And that's why active learning is quite prominent in drug discovery. So we can, if we're like doing simulations, we can of course generate our own data, which makes life a bit easier, but still it's quite expensive computationally. So active learning takes a bit of a different route than standard machine learning, where you basically have a predefined data set and say, okay, you kind of the pressure is on you to select the data set in a way that it's representative of the final application you're trying to solve with your machine learning model. With active learning, you're kind of taking away the pressure to some extent, such that the model basically decides where it's still uncertain and where it needs to still improve. And it's kind of telling you that using a uncertainty quantification method. So here in the active learning workflow, you need one more component. So let's say you have an oracle, which basically is the way that allows you to label the data, which could be a human. In our case, it's the docking method. So that is kind of assumed to be the ground truth, which, as Cristian already said, is somewhat of a stretch for docking, since it's not super accurate with respect to experiment, that for this lab here, we assume that our docking score would be the actual the ground truth. Then we need our machine learning model, which works as a surrogate function. And the main purpose here is to use our machine learning model as a surrogate model for the more expensive docking simulation. And finally, we need an objective function, which basically tells us which of these new compounds we would like to label, which give the model the biggest boost in accuracy if we are able to label this compound. So for this lab, this is going to be very simple, like pure active learning, meaning we are only caring about the uncertainty of the model, and we're labeling the compounds where the model is most uncertain about. However, this might not be the most realistic case because, let's say, for this docking screening, we're not really interested in having a model that is super accurate for very low binders or weak binders, because we don't really care if it's like if the binding affinity is like 1 kcal or -1 kcal. It's all bad, so we're not going to consider these molecules. We're more interested to have a model that is accurate at very strong binders and making sure it's predicting strong bind as well. So of course, there's still room for improvement, but for this lab, we're just going with the easiest way and say, just want to make our model better by selecting the highest uncertainty labels. So here's kind of the setup for the active learning framework. So we have like a starting seed pool of labeled data. Usually just selected randomly, or maybe you have some more insights or an existing data set. You can basically use all the data you already have. Then you train your machine learning model on this data. And then you have some uncertainty quantification scheme on top of your model, which allows you to not only predict the most likely binding affinity, but also the uncertainty that is associated with that prediction. And if you have this, let's say, UQ-aware model, you now run this over a large pool of unlabeled data, which are like possible compounds you might want to run docking on. And this allows you now to select the top uncertain compounds, which you then would usually remove from the pool of unlabeled compounds, then run this through our docking engine to get the labels. Now add these newly labeled compounds to the training set, and then just retrain our model on the new data. Since active learning usually runs in a low data setting, as Cristian already mentioned before, and usually we train on the full training data again. If for some reason our model is super expensive and we have a ton of data, of course you might want to reconsider and do like a trade-off between full training and fine-tuning, but obviously that's more of an engineering choice. So as I said, for this lab, we're just going to go with the easiest one. Our oracle, as I said, is the SMINA docking engine. And what's next to like build our active learning cycle is we need to define our model and the objective function. For the objective function, already teased that, just going to take the maximum uncertainty that our machine learning model is going to predict. And to make our lives easier to get an uncertainty-aware machine learning model kind of out of the start, we're using a Gaussian process where you kind of get the UQ prediction as a byproduct of your normal prediction. And kind of to be consistent with the lab yesterday, we're just going to use the ECFP fingerprints as our input to our Gaussian process surrogate model. So I'm just going to go ahead and run these cells here because we've seen that docking is quite slow in Colab. So I'm just going to give the active learning loop somewhat of a head start. And then I'm going to go back up and show you exactly what we've implemented here. So as I said, we need to start our active learning with a pool or like a first seed data set. And here we just went with the most simple approach. We kind of just really randomly select a subset of the data set, which we return here and use that as our initial samples where we use the docking. And then this is the initial data set we use for the active learning. Here you can see how our pandas data frame looks like, where we have the library stored. Unfortunately, here from don't have the best resolution. Just want to point you at 3 important columns. One is the predicted affinity. That's kind of where we store the predictions of our Gaussian process surrogate model. Same for the uncertainty. Here we just store the predicted uncertainty of the Gaussian process. And then here's the true affinity, and that is not like the true affinity of the experiment, but just our docking oracle prediction. These here are all NA because it's like the unlabeled pool data. We don't have any of these predictions yet. So next we need to build our Gaussian process surrogate model. For that, we once again went with the easiest option and just used scikit-learn for that, where we have a Gaussian process model and we use a radial basis function kernel. So in order to train the Gaussian process model, we're kind of retrieving all the labeled data that we have already. So here's just a very simple pandas manipulation. So we kind of select the fingerprints, meaning the descriptors, the molecule descriptors, for all molecules where we already have our docking score, because here we say that the sampled index needs to be bigger than equal to 1. And here this data stores basically in which active learning iteration we acquired the molecule. So if this is like 0 for all unlabeled ones, and we're only grabbing ones for which we have a label. That's kind of the input for our model. We also need to have the output for our model. That's the same way. So now we're kind of retrieving the true affinity from our docking engine, once again for the same compounds. And then finally, now that we have the input data like X and Y, we can just fit our Gaussian process regression. Here we're setting the hyperparameters of the radial basis function and pretty much just go from that. Now with this function, we already have our surrogate model. Now, as we said, the next step is we want to predict the affinities and the uncertainties for the pool data set that is still unlabeled. And this is what this function does here. So now we're retrieving all the molecules in our pool data set, or more specifically, the fingerprints, which are the input for the Gaussian process. Then we use our pre-trained Gaussian process, just run it forward on this input, which gives us the mean, which is the predicted affinity, and the standard deviation of the predicted uncertainty. And then we just save that into our pandas data frame. Lastly, we need the acquisition function, which basically tells us which molecules to sample next. We once again went with the easiest option. So we're basically just sorting our pandas data frame by the uncertainty. You can see here. We want to have it in a descending order, meaning that on the top, we will have the largest uncertainty compounds. And then we just return the sorted data frame. Now, the next two functions are more like utility functions. Since SMINA kind of predicts a SDF file for the ligands, here we just load the SDF files to get the poses that SMINA predicted. These are usually several poses per ligand. Then we just sort these by their affinity because we're just interested in the maximum binding affinity pose. And these values we then kind of append to a list and return these values just to kind of get the values that we need out of the SDF files. And finally, once we have retrieved these values, we're just going to restore it to our data frame. Now, the kind of setting the labels for the true binding affinity predicted by SMINA and setting the iteration by which we acquired these labels. So yeah, that's pretty much all we need for our active learning loop. Here's now just how we combine it. There's a couple of hyperparameters we need to set. Here we are setting the number of active learning iterations we can afford. Here we just set 5 because on Colab we don't have really much power. We're also saying the active learning batch size. Usually you're kind of doing this loop not for every ligand. In general, if you want to be most rigorous, you kind of take this active learning loop for each ligand, but that's in practice not super efficient. So here we just take 3. In practice, this might be much bigger than that, which also introduces more problems. But here we once again went with a small batch size to avoid these kind of problems. Just some hyperparameters, and then let's jump right into the active learning loop. So in the first iteration, as I said, we don't really have any labeled data yet, so we just select random indices which we want to label. Then we create some folders just to make sure we can save the predictions of SMINA. Here we're doing the actual docking. No, actually, here we're just retrieving the molecules we want to dock from our data frame. Here we're doing the actual docking, give it the molecules to SMINA, and then store these values into the SDF files. Finally, we're retrieving the predicted binding affinities from SMINA with the get results function from above. We're printing the affinities of the samples we extracted, and yeah, just then once we have those, we save it in the pandas data frame again. Now that we have gained more labeled data, we can now train our Gaussian process, train it on the labeled data. Then we run our Gaussian process forward on the unlabeled data, predict the binding affinities and the uncertainties, and then call our acquisition function to get the maximum uncertainty conformers for the next cycle. So we're going up again with these indices. We're gonna call Mina again and kind of keep iterating. So here you can see the progress. It's quite slow, as you see, but at least we can see the first iteration already. So this is all the random indices that we selected. Then we're calling Smina for these 3 ligands. And we should also print the affinity values somewhere. Yeah, here they are. So since this is a library that is designed for binding to this particular type of protein, these affinities are quite good. Then we run our Gaussian process and we get new indices, and I think we should print them somewhere as well. Yeah, here they are. So these 3 ligands now have the highest uncertainty for our Gaussian process model, and now Smina keeps running, but now we're kind of out of time to see any more results. So yeah, at that point, I would actually already ask for some questions if you have any about the active learning loop. Here it's really the most simple one. We're going to discuss how we could and should probably extend that.
Any questions?
Sorry, I just have a quick question. How did you choose your batch size again?
Yeah, that here it's just basically a random number, how much we can afford here on Colab. In practice, the smaller the batch size, the more accurate your active learning loop is, because the uncertainty, of course, changes whenever we have new data acquired and we retrain on it. So, but in practice, you would also have like a larger batch size in the sense of your Oracle often works more efficiently if you run for several things in parallel. Let's say we had we're not running on Colab, but we had 1,000 GPUs at disposal. Probably we want to use them at the same time. So we're going to have a much larger batch size, which then brings us into other problems for these small batch active learning. Probably this loop is okay, but if you have large batch active learning, you would want to make sure that the samples you're sending to your Oracle are not super correlated, because chances are, if you have a very large database and your model is just very weak for some kind of ligands, it's going to select out of these 1,000, maybe 900 from this one type, which is not going to efficiently improve your model. That's why there is a lot of development in large batch active learning, where you could do some kind of clustering on your pool data set, and then you make sure to kind of iterate over these clusters, and then yes, have a diverse set of high uncertainty ligands to then push to your Oracle, and then you can keep iterating that.
Gotcha, thank you.
Hi, at the top of the lab, it said active learning / Bayesian optimization. Now it just says active learning. I think this is commonly confused. Can you just quickly define what's Bayesian optimization for you and what's active learning for you? And what are we doing here?
Yeah, so here we're doing pure active learning. We put Bayesian optimization at the top as well, because that's what you usually want to do. We don't want to select as we said, we don't want to generate a model that is very accurate for very weak binders. We don't really care about those at all. So additionally, since we're doing some hit to lead screening, probably be interested in quickly finding a compound that binds well to the target protein. And that's why you usually want to have a balance between exploitation and exploration. Here for active learning, we're just doing exploration, but just looking for places where our model is not good yet, and then we're kind of trying to label that to improve our model. But in a Bayesian active learning loop, you would try to balance that, and at the same time improve your model by exploration, at the same time exploit the high value areas in your data set to find your ligand that you're looking for. So kind of exploit the high binding affinity regions. So yeah, here we're just doing pure active learning, but down on the Outlook, I'm going to also discuss a few acquisition functions that are more in the Bayesian optimization framework. We also do some exploitation.
Any other questions?
Just a quick question. You mentioned that, and it makes sense, you're not very interested in the low binding region. But if you don't have at least some precision there, don't you run the risk of getting too many false positives?
Yeah, sure. So if I'm saying we're not interested, that's not true. Obviously, like if the, let's say we're predicting binding affinity of -1 kcal, -2 kcal, let's say in our uncertainty estimate is ±3, then even in the best case, we're going to get like a binding affinity of -4 kcal or so, which is far too small. So within the uncertainty prediction of our model, we can say, okay, we can avoid that. But you're right that if our uncertainty is very bad and we say we're predicting -1, but it could be ±10, then of course we can't really draw much conclusions there. But at least like within the bounds of the uncertainty estimation, if we're confident that even in the best case this thing is not going to bind, then I think we're good. There's another one.
Do you, sorry if this was discussed already, but do you have an idea about how long it would take to do like an exhaustive search for these kinds of problems, like for like a practical kind of drug problem?
I mean, it's hard to say since it like depends on the size of the library and so on. Like, I can't give you like a very good estimate, but for compute clusters where you're parallelizing over a lot of CPUs, you can do much more than we're doing here on the Colab. But yeah, it's hard for me to give you a definite answer.
Okay, thanks.
Okay, great. So if that's kind of clear, then I will just continue and give you like some kind of outlook where we could go from here, since this is like the most basic implementation of what we're looking at. And yeah, if you're interested, also give you some pointers if you want to get your hands dirty with coding, how you would like to continue from here. So what have we done in this lab too? Cristian before kind of introduced you to the structure of the EGFR protein and kind of walked you through the preparation of the protein itself and the ligands. He also talked about how we can get the binding box for our SMINA docking engine. Then we've actually run the docking and analyzed the result. Then I've taken over and we've created a very simple Gaussian process model to predict the binding affinities much faster than the docking engine. And then we've kind of built an active learning loop to quickly optimize the surrogate model. So where could we go from here? In principle, classical docking and especially the first talk today of Gabriele already introduced you to a diffdoc, which is a diffusion-based or machine learning diffusion-based model to predict the binding poses. This can and kind of the field is evolving quite quickly in that regard. So in the beginning, they were a bit struggling to get physically good poses that were competitive with like the classical engines like SMINA, but now we're almost there, I would say, to get even better accuracy than these classical engines. At the same time, there's some potential for speed up because they avoid the kind of the handcrafted optimization engine of SMINA. Obviously, the docking quality highly depends on the docking score we're using. And this is really highly empirical. These, as Cristian already mentioned before, these are like physics-inspired functional forms, and they're kind of fitted to PDB bind to get the job somewhat decently done. But there's definitely room for improvement of those. And there's a very active research community trying to train machine learning models that give better docking scores, which then allow you to get better predictions of the binding affinity and also ideally get you better docking poses. Finally, there was a lot of buzz about AlphaFold 3, obviously. This could also be a big help for docking, because here for docking, we always assume to have the holo structure of the protein already given, which in practice might not always be the case. And AlphaFold now, by being AlphaFold 3 now being able to co-fold the protein and the ligand, it's kind of creating a somewhat decent, and there still needs to be research how well this holo structure works in practice, but it gives you at least a better estimate than just using the apo structure of the protein, for example. So that's definitely a few areas where machine learning can improve docking a lot. Nonetheless, docking has some implicit limitations. We've been talking about free energy perturbation and kind of free energy simulations before. You've seen that protein ligand binding is inherently dynamic and adaptive in nature. So by just getting one pose where the ligand is optimally docked is inherently limited in the accuracy you can get from that, just because the protein can move away again and explore some local minima close to the docking, and therefore, like, even if you're able to dock the ligand in this one pose, maybe the protein is going to move and push the ligand out again, and then you haven't won much. Also, I think I briefly talked about scoring functions before. So they kind of need to strike a balance, because they should be cheap to compute, because you want to like screen a large amount of ligands with that. At the same time, we have a lot of problems with these scoring functions. They're not as good as we want them to be. Yeah, there's a lot of like post-hoc research as well, like how well do these scoring functions actually predict experimental binding affinities, and they actually often correlate quite poorly with that. Also, SMINA might give you like reasonable docking poses, but the docking pose that is associated with the highest docking score is quite often not the actual correct docking pose. So yeah, always some problems with that. And as I said, machine learning docking scores try to improve on that. We also covered the next point to some degree. So as Cristian already said, blind docking is quite a bit more expensive and also more difficult than when you know the binding pose already. And therefore, like, finding the binding site can be a challenge if you don't know it already. And there are a couple of machine learning methods that also try to predict that. Finally, input preparation is a big problem still. So protonation states, for example, can be somewhat tricky to get correct. And these obviously highly influence the docking results you're getting. Also, like, PDB can be quite sometimes your protein is somewhat corrupted and so on. So it's always a good thing to like check your inputs carefully. Kind of to summarize these limitations here, as you see, docking is only like a very coarse method. Overall, like, that's like a paper that is like 10 years old already, but here they found like the predicted binding affinity has like an error of almost 3 kcal from the experimental values. And here you can see the scatter plot for Wiener predictions compared to experiments. And you can see here there's definitely still a lot of room for improvement. So what can we do if we need more accurate results? And at some point we definitely do. For that, we can resort to like physically rigorous approaches to simulate the binding for energy based on molecular dynamics. As we know, the binding affinity is quite a complex property. It's highly dynamical. It depends on the protein-ligand interactions. It depends on the entropy of the protein and the change in entropy of the ligand. Solvation effects play a role. All of that is not really covered in docking by only considering a single frame. And to overcome that, we can run free energy simulations which model all of these effects. Especially alchemical free energy simulations such as free energy perturbation have been really successfully used the last decade. And that's really the first decade where it's been able to run these kind of simulations in a more common way. So it's a very common scenario nowadays for pharma companies to run free energy perturbation. Before that, it's been still too expensive, but now we're finally at that point we can do that. So what's MD and free energy perturbations? I can't really go into all of the details here. That's for a large of a topic to cover here. Overall, with MD, we're trying to sample the Boltzmann distribution of the protein-ligand complex. And then for alchemical free energy simulations, we're kind of continuously turning off the interactions between the ligand and the protein. to estimate the binding free energy. But of course, in practice, it's much more complicated than what I make it sound here. When we're on the topic of MD simulations, just to like make the bridge to the talks you heard earlier today, the simulation accuracy, of course, depends highly on the force field that you use to describe the intra and intermolecular interactions. And we've already heard that classical force fields are reasonably good or moderately good at doing that. But for example, from Gianni's talk, you can see that even just using a neural network potential trained on ab initio data for the ligand can, to some degree, boost the binding affinity predictions you're getting from these simulations. At the same time, these neural network potentials are much more expensive than classical force fields. So to make another bridge, we definitely need some enhanced sampling methods if we want to make that working in a more commonplace approach. Just because we can, let's say, run like 10 ligands or so per GPU per day through FEP, we can't even do one with a neural network potential at that point. So there's still a lot of research to be done to accelerate that. To finish the cycle here now with active learning, since this is like super expensive still free energy perturbation, but much more accurate than docking, active learning free energy perturbation is actually quite a hot research area at the moment to kind of reduce the number of calls to the much more expensive oracle of free energy perturbation and kind of train a surrogate model to avoid or to more or less accurately predict the binding free energy and only call the FEP when it's strictly necessary. So yeah, that's kind of the more outlooky part on the physics part. On the active learning part, there's also a lot we can improve from here. One thing I already covered before on the question is like the question about small versus large scale, large batch active learning. So for small batch, the loop above is somewhat okay, but for large batch active learning, you really want to consider some clustering on your pool data. Also, the surrogate model is like the most simple surrogate model you can think of, like a Gaussian process just on these fingerprints. However, there are definitely more expressive models we could use to have a better surrogate model here. The binding free energy obviously depends highly on the 3D structure of the protein ligand complex. However, here we're just really inputting the fingerprints for the 2D fingerprints of the ligand. We don't have any information about the binding pocket or how the ligand is docked and so on. So there's obviously a lot of room for improvement to include this 3D structural information, which Cristian already mentioned in the introduction before. We could use like something like SOAP or ACE to get some 3D structure information into our surrogate model. If you want to get really fancy, you can, of course, also use like a pre-trained graph neural network, like equivariant graph neural networks such as Maze, Allegro, or whatever is your favorite one, and use these descriptors as input to your surrogate model. Then probably this would also improve the accuracy of your surrogate. Finally, this is also a question that we had before, the active learning itself. So here, this was pure active learning. So the acquisition function was just maximizing the uncertainty. However, as I said, this might not be the most practically relevant case because here active learning learned about exploration of the model and reducing the uncertainty of the model for the whole pool data set. However, we're more interested in finding a good binding ligand more quickly. So we should kind of balance the exploration and exploitation. And for that, we can use somewhat different acquisition functions. For example, one more interesting acquisition function is the probability of improvement. The formula is given here. So here, the mu is the predicted mean of the binding affinity. F of x plus is the current best estimate of the best ligand we have and the binding affinity of that. And eta here is like a tunable parameter that trades off exploitation and exploration, and sigma is the uncertainty. And if you quickly think about that formula, you will see that this gives you the probability that the ligand X is going to improve on your current best ligand. Expected improvement is a similar thing to that. here we're not only considering the probability that the next ligand will improve about our current best, but it will also include how much we can be better than that. I'm not going to go through the full formula here, but here you can see like the formula for the probability of improvement from above. And then here you can see basically the expected improvement. The final one I want to discuss, since it's a very straightforward one and often used one, is the upper confidence bound. So here we're kind of assuming that here the mean is what we're predicting, surrogate is predicting, and then we're adding one standard deviation of the uncertainty, which is kind of a best estimate. Let's say if you're lucky and the ligand is even better than our model predicts by mean, then this is what we could get in if we're lucky. So yeah, that kind of concludes the section I had about how we could improve the active learning loop. If you now want to get your hands a bit more dirty with coding yourself, here are a couple of suggestions where you could continue from here. First of all, like quite obvious, we could implement one of these more interesting acquisition functions and go from active learning to more like a Bayesian optimization scheme. If you want to do that, actually, there's a quite fancy library called ModAL, Modular Active Learning for Python. I think you might want to check it out because they already have a lot of acquisition functions implemented there. We already covered that as well, so you might be interested in building a more sophisticated surrogate model, maybe a neural network, maybe some 3D representations, including that. So I think you can pretty much go crazy here. And finally, like to connect to lab 1 as well, like you already screened down to like these 100 molecules. Maybe you want to like just push your SMINA docking engine now and kind of get the top 100 molecules from the docking from these 100 pre-screened ones. And yeah, that pretty much concludes the lab 2. And now I'm looking forward to any open questions and possibly some discussion.
All right, any questions for Stephan? Here.
Quick question. I might have missed it, but how did you train for the binding affinity predictions? Is it from experimental affinity?
No, here we just assume that the affinity predictions from docking engine would be the ground truth, and we say that's the best our model can do.
Got it. How
So
do the docking engines predict the affinity?
I can go a bit up again. So it's a very empirical function if you want. It's basically giving an estimate about the interaction energy, and then they're fitting a function to that. So here's the docking score C, which is kind of composed of pairwise interactions between the ligand and the protein, also pairwise interactions between the ligand itself. And then you're kind of dividing that into the intra and intermolecular interactions. You're only considering the intermolecular ones. And then here it's just a very straightforward formula. You kind of rescale it based on the number of rotational bonds in the ligand. I can zoom, yeah. I'm not sure if I can zoom. Hope it's a bit more bigger. Because as I said, the entropy of the ligand plays a role, so we want to like correct for the number of rotatable bonds, and then this W is basically just a value that has been fitted such that the predicted interaction energy is somewhat predictive of the binding affinity from experiment. And here they basically just trained on PDB bind and fitted these values.
Cool. If we could just hang in tight for a few more questions, and then that'll be the end of the day today. Thanks, everyone.
Hey, thanks for the presentation. I'm just wondering, like, when you said that there's like a mean absolute error of 2.85 kilocalories per mole. So like, I've actually seen that come up a couple times today. Like this kind of kilocal per mole energy error stuff. I'm just like, I have difficulty kind of understanding how bad that is. Like, can you give some intuition about how to interpret these values? Like, I get that having a more energy error is bad because it means you're worse at estimating the energy, but I don't know. Thank you.
Yeah, so kind of the binding free energy here is related by this formula to the ratio of bound to unbound ligand complexes. So, and here you can see there's a logarithm. So this is like exponentially bad. So you can do the math here, but I'm just going to give you like a rough estimate. Like 1 kcal per mole is like a factor of 5 to 8, if I'm not mistaken. So if you have an error of 1 kcal and the true ligand binds 10 times better than another ligand, then you're kind of predicting a fact. You're predicting it could be anything between 50 times better and 2 times better. That's like a 1 kcal difference, and for a 3 kcal difference, I think it's like a factor of, if I'm not mistaken, something like in the 200s or so. So that tells you you can't even just distinguish which one is the better binder at that point.
So kind of the way you talked about, obviously this is more exploration based in this active learning regime. I'm wondering if it's worthwhile playing around with hyperparameters related to docking, like exhaustiveness scoring or something more robust than the Gastiger charges. I'm just curious what you have from your experience on this.
Sorry, can you repeat?
So like the charge parameterization of your input molecules, or the exhaustiveness setting, saying like autodoc Vena, how funneled you are with respect to finding your pose. Is that worthwhile looking at as a hyperparameter, during this search, or is that just added cost from your experience?
Yeah, I'm not too sure about that. So since the accuracy of docking is anyhow quite limited, probably it's an important hyperparameter, but probably people have already explored that to some degree, which one are the best. I'm not sure how much value you can get to tweak that on the fly. Yeah, but I can't give you like a more definite answer.
Any other questions?
It's one at the top.
Oh, sorry.
Does the docking have applicability domain with respect to the ligand that is co-crystallized with the protein?
Maybe Cristian want to take it.
Is there an applicability domain for docking? Like the closer to the co-crystallized ligand, the better the docking score to predict affinity?
So if let me rephrase to understand if I got the question. If we dock something that is close to the real docking pose, if it is a better scoring, if the ligand is better scored, like
that's it. Like, is the docking score as good on the whole chemical space, or is it better if you're closer to the ligand of the initial
of the PDB structure?
Yeah.
I'll say for most of the biological chemical space is good enough. It is good enough. The docking score that you get is something completely empirical and changed by basically binding site to binding site, because it depends on what kind of physical interaction do you have. If you want to boost basically the docking score, you can just get a binding site with a lot of hydrogen, a lot of H-bond interaction, and you're gonna boost completely the docking score. So it's different between different kind of sites.
Just to add, kind of to reply you from a machine learning perspective, the applicability of the docking is not limited. You can apply it whatever the chemical space. The problem you might encounter is accuracy-wise, like it will depend on the chemistry you have, the protein you have, how well you represent the protein, and all the stuff that Cristian have done on preparing the protein. If you do that wrong, your docking won't be accurate. It will never be accurate anyway. But yeah, the less you take care of those pre-processing steps, the less accurate it will be. So, any other question?
On the topic of like the applicability domain of docking, because typically, especially when you see like with things that are based or enhanced with deep learning, essentially like GNINA, for instance, or NINA, I guess, depending on what you want to call it, it tends to do better on things that resemble very closely the proteins that came from like the PDB bind database. Like it'll actually be more correlated with experimental values of like small molecule bioactivity if it's coming from the actual thing, as opposed to having like, evolutionarily homologous things that are just different but weren't in the training data set.
What's their question? Or
That wasn't a
All
question.
right, right.
I think like he was just making the decision between classical docking and
Yeah,
ML-based docking. So, any question? Let's thank the speaker once again, and then.
All right. Thank you, everybody, for joining us for day 2.